That's interesting, by the way. So I have to change a bit my introduction, let's say. Let's do it. It's okay. Thank you for being here. And thank you very much, Rob, for this, I don't say nice invitation. So it was challenging, I have to be honest. I was like, okay, let's accept this let's do something different from what I do, like usually. As I told you already, but maybe everybody knows. So as a mathematician, I just enjoy mathematics, doing mathematics. I don't need to find any motivation outside like my field, let's say. And every time I deliver my message, convey my message to among peers. So that's why I'm saying hello. It was kind of hard for me, challenging to find a way to sell my subjects, let's say, to sell my favorite tool in my research, it is association schemes. So maybe many people, not the people that are in this room for sure, but students like think about mathematics as something that doesn't have any color, rigid, colorless, let's say. So like usual sentence like white chunks and black boards. Even if maybe nowadays would be, we should maybe switch, it's more about black markers and white boards. So, but this is not true. So today, and this was surprising for me as well. So I discovered many connections with Platonic solids. I know that they were there, but I never realized that they're actually distance regular graph. And that means association scheme, as someone maybe knows. Okay, so we will see that actually behind symmetry, there is many times, most of the time, symmetry means regularity, but also efficiency and stability. And that's why often nature picks, goes for it, for this very nice shape, because they actually, it turns out to be the most efficient way to organize the matter. Okay, so what I wanted to say is the following. So let's go back to maths now. This was the introduction. So we can, maybe we should okay, done. Okay. So there are many animations, so you have to, it's an interactive one. So we can take some web of connections, can be also messy. This is not that messy, I have to be honest. I mean, you can, as a mathematician, you can understand there is kind of regularity here, even if we don't put color. But see, let's say this is meant for students. And so to highlight the symmetry, the regularity, I need, this is what I call a color palette. And my color palette is given by association schemes. So this is what I do then. So I highlight regularity in this way, if it's possible. Okay, look, this. Okay, now this for me represents some things. This is, I will explain you why we will actually construct this together. This is an association scheme. The first, maybe not trivial example, the easiest one and not trivial. We have 3 classes, 3 colors. We will see why. And actually this depends on distances that we can have, we say, in this graph. Web of connection, most of the cases are graphs. Okay, and now we'll just say, just listen to this sentence, but I will explain this. Actually, this color palette represents, mathematically speaking, a color partition of the complete graph that we can construct from an initial graph, like this, the hexagon. Okay, so keep in mind this. Okay, I don't know what happened. Okay, too much revealing, I don't know. Why? Aspetta. Yes, okay, let's start again. Okay, so I put this color. Yes, so as I said, nature goes for it. Like, okay, they are beautiful, but they are efficient, they are stable. And so that's why this kind of shape, like the hexagon, we will see other shape, actually often occur in nature, like in honeycomb or in snowflakes. Okay. Perfect. Now we have to understand what's the strategy, the criteria. How do we actually distribute these colors? Again, we will start from our favorite example, the hexagon. You can think like a social network, but actually I realize that it's better, I mean, since there are just 6 people there, okay, 6 of us. Literally there are 6 of us almost. So you can think of like, we are sitting around a table, not around a table, like a hexagonal table. And I want to understand, to understand the interaction that I have with the people around me according to the distance. The closest to me I will have, then I have like the 1, 2 steps away, 3, and maybe that's enough for this kind of graph. Let's see. So, okay. Again, as I showed in the previous slide, I will pick red for the neighborhood graph, we say. So what I do, so we can pick actually any vertex here and you can check. So I'm I'm coloring with red color the edges that take me to the nearest, like closer people to me. That's why I say also best friends if we think in terms of friendship levels. So this is the neighborhood graph. Distance it's one step away from me. Okay. And this is the true. We will also analyze this for any vertex here. Okay. That's how I distribute my color there. Distance 1. Then we proceed and say again in this table, of course, what about the people that are 2 steps away from me? That means distance 2. And here, then I will assign another color. So here, of course, I'm picking, doesn't mean that red means, okay, so within my context, our context, let's say, red will always represent a neighborhood, and blue, we will say, the maximum distance graph. And then we can pick any color in between. But what is important, you could also start with another color, your favorite one, your favorite palette. What's important is to use different colors to distinguish the different distances, or friendship level. That's why I say friend or friends here. Okay, so what about those that are the farthest in front of me, the antipode, I would say. Those are distant 3 steps away from me. And then I choose another color. Okay. This is how I distributed the color in the previous one. So I'm saying that this is an association scheme. I won't prove this because, this is not enough to say it's not every partition okay, so this is a partition, a color partition of my complete graph arising from the hexagon. But of course, to say that it's actually an association scheme, we have to check some further properties about distance regularities. But trust me, this is an association scheme. We'll explore partially this. In an association scheme, and this is what I'm highlighting here, in particular in this association scheme, whatever is the vertex that we take, so the person that we fix, we have to find always the same number of red connections, green connection, blue connection. This is what I'm saying. So this is for the vertex that I fixed here, but it's the same for any other. You can easily check. Okay. It's taking us to the way for understanding this association scheme. Okay. So again, this was meant to be for students, maybe it's still. Every time you see this speech bubble, to highlight something, to summarize, let's say. And in this one, like these golden ones, I put some technical tips. So how it should be defined, should be said properly. So what I'm saying, again, this is the third time that I say, color partition the edges of the complete graph that usually we denote by K6 into 3 classes. And so we say that the color classes form a 3-class association scheme because we have 3 sets of partition. But this is due to the fact of distance regularity of some graph that we start with. The cyclic graph 6, whatever, say the hexagon. You can also see it like a cycle. Okay. We'll try to explain this concept, just conceptually, this distance regularity property. Okay. We can go further. So till now, I just check, I fix one person in the room or around, like sitting at the table and checking the connection. So it's me there on the table and checking my connection. What now if we fix couples, pairs? How then a pair interact with all the other people sitting at the table? And that's the magic for me, the association scheme. So maybe the one that we saw till now was kind of visible to everybody. Nothing crazy about this regularity. But now it's actually where the regularity is kind of hidden and association scheme able to highlight this, to reveal this. So that's the question. One of the possible questions is just an example. So if we are in a blue relation, that's the thing, means that we are strangers, we are antipodal pair, let's say on this table. At this table, how many are red to me and green to you? I can also ask the other way around or any other color. So actually, this is what I'm doing. Let's see. Okay. So I pick any blue connection, blue edges, and I want to count this triangle. And I can see, like this is, because it is a very nice and easy picture to handle, like manually, we can easily see that for this fixed one, we have 2 triangles like this. So the answer is 2. But the magic is the fact that this is true for any blue pair. Okay, so again, so this kind of triangle, sorry, we are counting. So if we have, I don't know, distance 3, let's say like that, how many are a distance 1 from the first and distance 2 from the second? This is what we are counting. Yes, it is important, bravo. In this graph, no. But yes, in general it is, because this is a symmetric association scheme. Actually, this also means commutativity. So it means that whatever is the, so there is like, this is further regularity. Whatever is the order, I will always find the same number. Good. Okay, so let's continue. So this is again, because this is what it is like, let me convince these people in the room that it is like that. So I'm just turning now, I'm going around. So yes, it's a bit boring, it's also a bit slow. Okay, maybe I should stay here. I can stay here, maybe I can see better what I'm saying and doing. Okay, so again, you trust me, but so in this way, I'm also covering the other order, going through all of them. Okay, so the answer, as I said, doesn't matter which kind of two strangers we pick, but the answer is always 2. Okay, another example on the second one. Okay, what if, okay, now we are green, so acquaintances, friends of friends, and we want to count the common close friends, best friends. Again, let's check. So this is, what's the number here? You expect at this point that again will be a constant number for each of them. Of course, probably different, but could be also the same, and who cares? So what we are doing now is considering acquaintances and counting these triangles. And you can see this is the only one. And this is the same for any of them. Again, it's a very easy, simple example, but this is actually what is behind the association scheme more in general. This is for me the most practical way to see it. Okay, again, I did for every. Okay, yes. Yes, it was very hard actually, but okay. So again, no matter which pair, green pair we take, we consider we pick, again, we will always share just one guy. Okay, that's the general rule, idea. So if we are in relationship K or color K, now I'm just using, of course, we can use letters, number, whatever to enumerate those. If we are in relationship K, distance K, since we are considering distance regular graph mainly, in general, it's not necessarily distance regular graph. How many people are in relationship I with me and J with you? So that's the kind of triangle in general that we count in an association scheme. And the answer, since we are, okay, here, no. Since we are dealing with an association scheme, and these are examples that kind of should convince us, you should do it for every of these triple. In association scheme, this number is constant. It's always the same. Whatever is the pair that I start with. But let me say better. So what actually we are dealing with are intersection numbers. These are the most characterizing things of an association scheme. So that's why I'm saying I'm going beyond like just checking the distance from me. I'm checking the distance or whatever, like some kind of structure from a pair. Counting these triangles, colored triangles. So again, if our relationship is color K, this is the symbol, PKIJ, to represent the number of people, Z, such that the relationship between me and Z is I, and relationship between you and Z is J. Okay, here now I'm not like, I'm hiding this, but I'm not considering the order because I know that in this scheme, everything, whatever is the order we pick, as you observe, it's okay. So take it like that. It was to make it simple. Okay, that's the magic. The number, it's constant in this sense. So depends only on the distances, on the color, not on the pair that I consider. And that's beautiful for me. This is not. This is a definition. Yes. When we have an association scheme, then we attach to them a set of numbers, intersection number, that must satisfy this property. Yes. Okay. Actually, this is the crucial one. This is the hardest to check. How to check? So for an easy graph, we do this manually, you see. Easy. But it's still, there are many to check here. Can be kind of boring. At least just producing these 2 examples takes today. Believe me. But it's okay. Let's go. Okay. So that's what we are saying. So these are the numbers that we are computing. PBRG, PBGR, again, equal to. And here, these are the numbers, PGRR. Now, we have a notation for that. Okay, let's go on. Okay, we can, it's revealing. We could now move from the pictures, from these graphs, nice one, to the matrices. In this case, it's not needed. As I said, we could compute there these numbers, but actually this is powerful. Now we can produce a machinery. So actually matrices will help us to understand, to read these numbers easily. Because the matrices that now we will associate with these color classes, with these colors, they just reproduce the property, the combinatorial property. So this will be the matricial, let's say, algebraic counterpart of what's happening combinatorially speaking. Okay, so how do we attach to a color with a color a matrix? How do we build this matrix? This is the usual way. So first we label this because otherwise we get lost. Actually, I forgot to put, I should have put also labels here. We follow this way. And so what we do, first we have to pick, let's say, we can start like with all zero metrics. And we have to put some one, replace in some places 0 with 1. How? So first I index this matrix on 1, 2, 3, 4, 5, 6. So that every row column that I fix will represent one of my vertex. So the first row, okay, so I expect to contain 1 in which position? Those that actually here in the graph represent the red connections. So 1 has 2 red connections, these edges, that takes us to the 2 and 6 vertices. So I will put 1, replacing the 0, because I'm starting with this 0 matrix, put 1 in the second position and in 6th, and so on. This is how I'm reading and then constructing, let's say, this matrix. The second position, again, the second, row will then contain 1 whenever I find neighbors of 2. So 1, 3, first position, third, and so on, the same way. Yes, adjacency matrix. Again, this was like meant to be easy things. So I'm not even mentioning adjacency, but yes, adjacency neighborhood matrix. We can do this for every colored graph, not just for the, let's say, hexagon, the graph that is used in graph theory. Okay, so sorry, I don't need to spend so much time, but this is the same logic we're applying here. Again, so now I'm checking the green connections. So for example, in the first row, I will read 1 whenever I find a guy that is in green connection, green relationship, let's say, with 1. Third position, then 5th position, and so on. Also note that these matrices are symmetric because, okay, the order doesn't matter. So I can read also through the column, it's the same. And also, we check this. I will find how many ones, like 2, again, along the columns and along the rows, because we know that in this graph, we have exactly 2 red connections for each, 2 green connections for each. Okay, that same strategy here, not even explained, so maybe I have time to go over. Okay, great. What's then the secret? What do we do with this matrix? If we compute, and this is magic, if we compute the products, any products of 2 of them, even more multiple, we are able then to count, to figure out what this intersection number look like. This is theory again. So it turns out that when you translate what we see at the beginning in terms of matrices and do the products, they first of all they are linear combination of the set that we start with. We don't go further or outside, that's important. And second thing, since maybe you noticed, they don't overlap. So if I sum all of them, that's why they reflect the fact that we have a partition. If you sum all of them, you will get the all one matrix, of course, except the diagonal, because I'm not mentioning the identity. But if I put, okay, also removing. So summing them, actually, this corresponds to which matrix? The adjacency symmetry of the complete graph. So everything makes sense. Okay. Okay, this important property allows us actually to read, for example, if this works. Here, I compute, for example, this product. So trust me, you get this. But it's actually a general rule that every time we will get a linear combination of the guys that we have here available. And in front, we will read the intersection number. Which intersection number? The one that have RG, like subindices. Because actually, when you do this product, this is what we are doing. Entry-wise, we see picking 2 vertices, x and y, that are in any relation, and counting those that are red to the first, green to the second. Then I will see and read this number if they are in red relation. This in blue, and in green also should appear, but in this case it's 0. That's why it's not there. But usually this is like supposed to be the sum over all the colors. Fix these 2. Okay, let me just show you in the picture. This is the numbers that we are counting there, and it turns out, not right position. Okay, that this is 0. That's why I don't see, like, in the linear combination, of course, the contribution is 0 of a green. Is it clear? No. Okay. Really? Okay, this is the intersection number that we had before. Okay, so I'm saying that this is, okay, the scope, let's say, of this. So it's like, trust me, if you translate this in terms of matrices and you do the product, entry-wise, you see these numbers. So you don't need to compute manually on the graph. You produce a machinery. Okay, take it like this, okay. But still, this is just another example. I think we can go on. But again, it works in the same way, but now we are just counting. When I say AR squared, this is AR times AR. So again, any pair that I pick, X and Y, whatever is the relation, I'm counting entry-wise, that what this number should represent. The guys that are R to the first, R to the second, red to me, red to you. And here they're appearing like according of what we have to what we have in the graph. All the other numbers, contribution are 0. That's why. Ecco. That's why they're not appearing. Okay, so this is maybe better for you to sum up. Okay, this is the mathematical definition. So this is how actually we define association scheme. We can either define association scheme using color classes, so like the combinatorial, let's say, usual, I would say maybe the most common one definition, but this is for me the most operative one, the one that we see in the application. We make our hand dirty. We work with this, actually. Okay, so what is an association scheme? It's a set of matrices, let's say, that have this property. This is the property that I highlighted at the beginning. So when they sum all together, including the identity matrix, but I put 6 because in this case it's 6 times 6 matrices, then I get all one matrix. Because this is a partition of the adjacency graph, whatever, of the complete graph. They are symmetric, this specific case, let's say, and you can see, they commute, so trust me, they commute. And in particular, they commute, but these products look like that. So these are just application of what is actually required for association scheme. Every time I do this product, that's why I say it's an algebra if I add the identity. So even if every time I do this product, I stay in this set of matrices. Plus, and these matrices are multiplied by this pkij that I can literally like easily distinguish when I compute this because we don't have overlap. So I can see the contribution of these numbers. I don't know if it is clear, but kind of. Okay. No, this is always the notation, Sadmir. Okay, no power, not power. Yes, maybe I should have, yes. Yes, brown. It's okay, yeah. Exactly, because these are, for every ij fix, I sum for all the possible relation that I have between two pairs. Okay, maybe I should have put that, sorry. Okay, now since, again, this is just, we played a lot with this graph, we want to convince ourselves that, okay, as I mentioned in the beginning, I promised you that you will see association scheme all around after this lecture. Okay, then to do that, we have to produce more examples. And this is maybe one of the most famous one within graph theory, Petersen graph. Actually, I heard in a conference, this was funny, and I think I kind of agree, graph theory conference, it was crazy. And some guys realized that like after all the talks that they gave, like at the end of the conference, they say, it's crazy, like every property, a new theoretical result that we achieve, we'll have as an example Petersen graph. The answer is always Petersen graph. Also in this case, Petersen graph produces a very nice particular example, because now we will reduce our color palette to 2. Why? Because the maximum distance in this graph, this is what it looks like. It's coming. It's fading. Okay, this is Petersen graph, gray one, then we put color on it. Okay, again, I have to stay here. I'll stay here. Okay. Because it's always the adjacency graph that we start with, since it is adjacency graph, it's the neighborhood graph. It's the one that I will color with the red color. So this is how I read the neighborhood. For every vertex, we'll have, you can easily check here. So this is again taking us to the way of association scheme. So first thing to check, it's the valency, the degree. So it's a regular graph. Every vertex will have 3 connections here. Okay, and then as I said, now we have to distribute colors, but first we have to complete the graph to make this complete. So, and we are adding all these, and I'm saying that we only need, so all of them belong to the same set of colors. This is what we are actually realizing, because they all represent the connection, referring to the maximum distance, 2. in this case. You can easily see. Okay, so that's the main difference. If I compare this with the previous object, we have distance 2, that's the maximum. You can just see that any 2 points is 2 steps away. Starting from the red graph or the gray. Okay. So here, yes. I was like, let me just maybe split this picture so it's a bit, because it's getting nested now. Even if this is very highly, we say strong regular graph, highly regular. So more than a usual distance regular graph, but still it's getting nested, even if we have just 2 colors. Okay, so these are the main difference with the previous one. Now we have the main one for me is like the most important, because I'm just interpreting everything in terms of colors is this. So more vertices, but in any case, organized nicely. Okay, and of course, we don't have any green connection. Again, okay, so this is what we call an example of a strong regular graph that it's always described. This is enough, this one to say, trust me, enough to just know these numbers to compute all the other parameters. In this case, these parameters also characterized the graph. Okay. So here I'm explaining the meaning of these numbers. 10 is the number of vertices. 3 is the valency, as I said, the connection. And then, okay, this is like the role for me of the association scheme. So these are the intersection numbers, some specific one that kind of characterize this specific kind of graph. When it is strong, this is enough, this is what I'm saying, to compute all the others. So here, this is the so-called no triangle rule, red triangle. So if I pick 2 guys that are friends, how many guys are, how many friends we share? 0 is in this graph, the answer. You can easily see, we don't have any, you can see. There is no red triangle. Okay, and also this is the other way around. What if we are not, if we are stranger, how many we have in common? Exactly 1. Again, you can check from this picture. This is just another example. We will go back to this when we deal with some example in 3D dimensional space, because actually this turns out to be the shadow of a very famous, I didn't know that, by the way, okay. But yeah, so the shadow of a very famous Platonic solid. The shadow, let's say that up to some equivalence relation, we can see, we recognize in this Platonic solid, the symmetry in the plane of this guy. So keep in mind this. Okay, finally we move, as I promised, to 3D dimensional space. And this is for me the way to start, let's say, talking about bringing one of the most powerful family of association scheme within the concept of graph theory, but actually association scheme theory, the Hamming scheme. And the cube, surprisingly, let's say, is the first non-trivial example. So let's understand this family starting from the cube. Also, maybe also notice that I wrote here language of bits, because usually this is, let's say, the golden standard for coding theory. But not just this guy, the family of Hamming scheme. And so that's why we will label the vertices here in this nice particular way. We use bits. So we have our words, our vertices will have length 3, and we are dealing with an alphabet consisting of bits 0, 1. So now maybe you can understand. Okay, so so this is again the cube, and I'm saying that. Okay, great. Putting red color on this, as always, adjacency graph, neighborhood graph within my association scheme context. And in fact, you see, let's see if it is why did I distribute the vertices in this way? Because of course, now let's compare, for example, 0 to all these neighbors. What we notice? 0, 0 have neighbors 0, 0, 1, these other guys, these other guys. And if I compare with this, they always differ in 1 bit. So distance 1, the difference in 1 bit. And so we cannot understand that to complete this graph, what we need to check, to draw the face diagonals and the body diagonals. This is messy, so I did this for you. Very hard, I have to be honest, but I did it. There you go. You can't even imagine, but okay. So let's extract this graph so we see better. So I'm saying that in this specific case, in 3D dimension, this is the green scheme, graph. This is the blue scheme. Again, graph. Okay, so the green is the one that now should like represent the distance 2. Now we'll see with an example, again, with our favorite vertex 0, 0, 0 is the easiest. And this should represent distance 3. So I'm saying that since the maximum distance, you can see, because we have length 3, so they can at most differ in 3. They are completely disjoint. Okay, so let me explain this. How do I distribute this color? Why I'm saying that this is distance 1, this 2, distance 3. Okay, here we kind of understand the difference. It's just in 1 bit. Okay, let me see, because I don't see there. Okay, let's move then to the green one. If we, again, this works for any of the word that we pick there. But again, this is my first one, 0, 0, 0. You see, if you compare all the others the green neighbors, okay, they differ from 0, 0 in 2 bits distance too. Okay, I bet just easy. I know that here. Okay, I can then go faster. Okay, great. Let me go here. So now the same things apply, of course, for the this is so we have antipodal pairs because there is unique way to be different from this. And this applies to all the other guys that there are not mentioned, of course. It's not visible, but I see from here there is also a fourth one there behind. Trust me, the perspective is not like the most efficient one. Okay. Okay, here I'm just summarizing what I said. Okay, so this is the first very important representative of Hamming scheme that I wrote here. Again, this is just to create something attractive. This is how computers, let's say, okay, interpret, let's say, our world, the world surrounding us, at least in terms of signals, let's say. Binary codes and flipped bits. So, don't laugh now, but this is a nice example. Any company, space company, NASA, I would say maybe the one that everybody knows. This is how error-corrected codes works. What I mean, so if NASA receives or sends a message, I mean, to what? From where? Of course, NASA is communicating like daily, but not even daily, I think every like 2 seconds, with the world around us, not world around us, actually with the solar system, not even that, with interstellar space. I realized that in 1977, 2 very famous, I think, probes were launched, Voyager 1 and 2, to explore the solar system. Mostly the attention was focused on Mars, communication with Mars. So yeah, that's the thing. So when I say send message, it's like with the probe that are somewhere spread. Yes. Okay, so just roughly speaking, 0, 0, 0 can, because of some noise, because we have long distance, you can imagine. So something can get wrong, and so this can be kind of damaged, this message, and then turn in this one. But since computer, let's say, or whatever, the program there, recognize red relation, it will detect the error, and actually it will understand that there was 1 bit error, and will also be able to correct. That's the principle of error correcting code, self-correcting code. So this is roughly speaking. I will explain better on the cube, trust me. I know that maybe for you, what she's saying. Okay, this. Okay. But before that, let me scale the cube. Yeah, how much time do I have? Just stop me at a certain point, because I don't know. Okay, I don't know. I still have time, probably. Okay, so let's scale the cube. So what I'm saying such a thing, when I say scaling the cube, means let's kind of try to define in an easy way the Hamming scheme family. It's an infinite family depending on 2 parameters. So every time that I define an association scheme, I have to focus my attention on 2 things. Of course, the set of vertices that I'm playing with, and how I define these color classes. What's the relation between vertices? Okay, so in association scheme, this is our, let's say, world, okay, planet. So we consider as vertices strings of length n from an alphabet of size q. In the previous one, we had like 3 words. I mean, the length was 3 for the words, and we had alphabet of 2, 0, 1. Okay, and then how I define then this color class is the relation. I say the 2 words for an edge of color I, if they differ in exactly I position. So for the previous one, if we put 1, 2, 3, we get the cube. If we stop there, they differ in 1, in 2, in 3, and so on. So you can understand that we can extend this. Okay, so this is the usual notation for the standard n-dimensional pair cube. So if we fix q equal to, say it again. Yeah, for me, okay, whatever. You joke, great. Okay, so, and this is the standard notation for the general one. And we will see, if we have time at this point, that this actually can be used for describing complex data like DNA bases. They will blow your mind because this will happen to me at least. Okay, this is just a representation of what is called tesseract, or let's say easily saying a 4D cube. Of course, for the cube, we are not able to see this because we are not able to see the 4-dimensional space, but this is the 3D projection. And some architects had fun, let's say, building this, proving that, okay, these are nice, we can build them. Okay. Okay, so it's easy to see that then the size of this word is q to the n. In the previous case was 2 to the 3, okay? And the colors, the number of colors, so the palette, again, as I said, we have to pick n distinct colors. In the previous one, 3, and so on. Of course, then here means that we will need 4. Again, and so on. Okay, now, finally, because till now we just talk about mathematics, let's say, roughly speaking as well. So here I'm just saying that actually association scheme, at least this one, it's not abstract at all. It's in everything that kind of surrounds us. I mean, every time the NASA sends some message to Mars or talk to Mars, in any actually when we send message, we use 5G signal, whatever. It's always there, this association scheme correcting mistakes, error. But actually it turns out that if we extend our alphabet, this association scheme is also working on the basis of the DNA. Crazy, we'll see that. So by the way, so this kind of represents for me protection of information. Okay. Again, so let me go back to the cube and let's explain the concept of error correcting codes power on this. Okay, so we have the same structure here. Let me just, we extract this guy. Yes. Okay, now, before defining a code, in this context, it's kind of easy. We don't have so many choices. But just let's observe what's happening on this graph. Pick any 2 pairs that are antipodes. So any antipodal pairs, like this. Again, this is my favorite one. Okay, and let's check the neighborhood, let's say. So the neighbors around each of these guys. You understand that this is actually the set of neighbors, of course, of 0, 0. I don't need to explain this. Okay, notice this, and this is actually due to the symmetry of the association scheme regularity. These bubbles, let's say, they work like safety zone for what? Let's see. Okay, first of all, okay, this, what I represent here, just represent that PBRR is 0. So this number, what is saying this number? If we pick an antipodal pair and we want to count the neighbors, we will get 0. This means that there is no overlap. There is no common neighbor. That's great for coding theory. Why? So I'm saying here, if a bit flip, we know exactly how to fix it. Okay, let's say better. So if a message falls within this bubble, one of these, let's say in the bubble around 0, 0, 0, computer knows exactly what to do, how to correct this, and so it will correct any of the, I don't know, for example, we end up with 0, 0, 1, this must come from 0, 0, 0. Okay. Because I mean, why? Because I'm assuming that I will get to this. My code, favorite code, now we understand this, should be made of, consisting of words that are far apart, the furthest one. So in this way, I don't have overlap. That's why I say total safety. So if some mistake happens, 1 bit here, of course, we are able to reconstruct the original message. So here it is to summarize what I said again, NASA, but whatever. If we want to send safely a message, we need to pick a code consisting of code words that are far apart, like this. This is one of the biggest antenna on the planet. Again, this is NASA things, this is in Australia, and this is talking to Voyager 1. Again, so means talking to Mars. That's the meaning of Voyager 1. Probe, navigating there. Okay, so again, to convince you about the fact, if you pick any other, let's say, relation, you will end up with a failure. I mean, not always, but most of the cases. So let's check what's happening here. So if I consider as my code now 0, 0, 1, 1, 0, I have overlap of this bubble, neighborhood bubble, and that's the problem. So the fact is the following: PGRR is equal to 2. That's the ambiguity, the ambiguous, let's say, situation. If a message affected by noise follow in this area, we are not able to reconstruct the original message. Okay, that's the concept. Okay, so we don't want to pick this code. It's not a good code. Okay, it's not a code. Okay, so that's actually the technical tip that we need to know. Maybe most of you know that if we want to correct the errors, we need in our code this minimum distance, the distance between code words, to be at least 2 times plus 1. And at least also comparing with the t. So again, in our case, one error, t equal 1, will be corrected if we consider code words where t is equal 3. Now that's clear. That's why in this very restricted like environment, we will pick just, okay, we can just pick antipodal pairs. Okay, now here's some pictures just to say that, of course, like in background, this ME scheme is working like to protect our data. When we send a message with a weak signal, or WhatsApp works everywhere, in fact, and if we read as, let's say, damaged QR code, we are still able to read it because there is like this scheme correcting. For the old-fashioned one, maybe everybody saw this like some years ago. So also for Scratch, CD-ROM works like this. If they are not like heavily damaged, we can still read the track. Don't laugh. This was taught for students. Okay, let's go on. Okay, I don't know how much time I have, but okay. It's in any case a nice way maybe to conclude, almost. Okay, I promised you that if we extend the alphabet, then we can actually see DNA with different eyes, at least understand that actually life operates within the context of association scheme. Which scheme? Okay, let me, again, I have to stick to this position. Okay, great. I'm saying what I say, like operates in this HC3-4 Hemming space. What does this mean? So DNA, but actually RNA, when duplicates or transcription, like transcript, let's say, translate information, uses an alphabet of 4 letters, the 4 bases. Everybody maybe hears, like, knows about from like chemistry class, I don't know. So these are the bases in the double helix for DNA, and this is the single one, but they are the same. So whatever, I can consider the ME space depending on this alphabet or this alphabet. You see, actually, the only difference in these two, uracil, timing, whatever, but it's the same. The other are the same because while transcription, during the transcription, somehow uracil turns into timing. Just trust me. I checked everything. So again, our alphabet is then, let's say, for this, let's stick to the DNA notation, is made of these letters. This means bases, combination of them now. How do we combine this? We could make it even like harder, of course, so playing with longer words, but let's stick to this very nice, easy example. So our words are the following, are words of length 3 with 3 letters. They are called codons. And I didn't know that. Actually, codons are the code, are the recipes for amino acids. And amino acids are nothing that like building block in our body in the sense that they are the responsible of the building of proteins. Maybe some of us kind of had this knowledge, yes, by the way. So we are building proteins starting from bases, okay? Every 3 of these represent some amino acid, but actually that's now the very smart things that nature did. So there are 20 of the amino acids, okay? But here you kind of understand that we are handling, we are like available more combinations. Okay, let me again here. So we have 64 words. Of course, again, the color, now we know that it's 3 because this guy is 3, simply. We don't need to check anymore because we have this machinery for association scheme. Okay. So let me explain this. Why actually did nature pick 3 letters? Oh, because if n is equal to, trivially, using this combination, like combinatorial formula, of course, we will have 16 recipes, not enough for the cake that you want to make, let's say. Okay. But if n is equal to 3, then we get 64. And this is what is called redundancy buffer, or actually redundancy safety zone, net. What does this mean? Okay, now we'll explain what everything. This gives extra space, extra room to our body. Let's say actually someone else for us, the one that has competence in our body, we say repair or repairing enzymes, to operate as a self-biological, let's say, error correcting code or system. Okay, so we have extra space, extra room. What does it mean? That some of these combinations will correspond to the same. And this allows me to have space to make mistakes and correct. So that's why every day, even if we expose ourselves to UV, because these things, all these things that surround us cause mutations. But these are what we call silent mutations, because our body is able to detect a mistake, fix it, and say, whatever, even if this like that, because we have more codons for the same amino acid. So equivalent kind of, I say, similar recipes for the same result. Okay, this is again roughly speaking. This is more technical. Again, so this is the criterion, mapping many to one. So actually, if you Google this kind of amino acid, this is crazy. There is a list and there is like, these guys correspond to this amino acid. These other guys correspond. Mainly, we have that 4, 2 or 6 of them represent the same amino acid codon. So different codons for the same amino acid. Let's take this example. For example, it turns out that glycine can be obtained. Let's say originally we refer to glycine with GGA. But if due to some noise, UV rays, chemicals, heat, we get mutation during the transcription, if we end up, let's say, in this set, we will still be able to read glycine, our body. This is how it works. And I wrote another thing fundamental here. So this is like the intelligence of nature. Nature prioritizes, let's say, the third position of the codon because it's the one that is affected the most by mistake error, by this noise. So that's why it's like every time we have 2GG, we will get glycine, whatever is the letter here. So mathematically speaking, in terms of code, so most of distance one errors at the third position can be fixed. So here I have just a nice representation animation for this. So this is our cluster, save it to one. Yes, we will get also the glycine. So whatever is the message that we start with, let's say GGA, if we change to any of these, the result will always be staying the same. For me, this is beautiful. But then I asked myself, Google, and I was like, what if we have changed somewhere else? So, and this goes beyond ME scheme, let's say, at least the one that we use in our computer. There is another thing that is called mitigation of the effect. So if enzymes can repair, let's say, can't repair mistake, because maybe we have changes in this first part, so we are not able to control that, but still, this mitigation effect is made in such a way, nature organized that the other neighbors of this structure that I didn't mention here, so I don't know, another neighbor of GGA, so we go out the safety zone, is, I don't know, GUA. This is another amino acid at that point. And this is valine, but whatever. Valine is kind of very, chemically speaking, similar to the one that we start with. So it's not a big deal. That's thick. Okay. So of course, in the worst case, when our system stops working, we get disease, cancer. That's it. That's why. To conclude. Okay, great. I hope I convinced you about the utility of association schemes, at least ME scheme. But now, I don't know if I have time, but the beauty is actually hidden here behind the curtain of Johnson schemes. So Johnson schemes, I didn't know that, but it's related to some combinatorial question that I will display now. Design theory, in fact. This is like the father, actually the master of that theory. But I realized that all the 5 Platonic solids, we know that there are exactly 5, it is possible to prove this, are kind of related to Johnson scheme. Some of them are some Johnson scheme, some other association scheme that in any case, when you project on the 2D plane, you will end up with a Johnson scheme shadow. Beautiful. I don't know if I'm clear, but what I want to say, whatever is the Platonic solid we consider, we can see somehow a Johnson scheme. Okay, so these are the questions, very trivial one. Maybe you already asked yourself about this, I guess. So we start from a population with people. How many groups of K people can we form out of it? Classical question, binomial number, and so on. Okay, and again, how do this, because that's for me most interesting, let's say maybe not so immediate, how do this group, K groups, interact? Again, I'm saying here, so trust me, the answer, yeah, of course, sits in some combinatorial things, but sits within the context of an association scheme. It is the Johnson scheme. Okay, to understand this, let's try with an example, the easiest one. So we have 4 people, population of 4 people, 1, 2, 3, 4, and these are all the possible pairs. How do we connect these pairs? Okay. And I will explain why. So I'm saying that this is a way to represent the graph, the neighborhood graph, once we have these vertices. In fact, if we consider 1, 2, but any other of them, so let's check if it is fair. What are the neighbors of 1, 2, 2, 4, 2, 3, 1, 3, 1, 4, and so on, almost all of them. So if you compare any of these with this, we'll share either 1 or 2. So we are saying that the neighbors are those that have one element in common. So we expect, of course, then how do we complete then the graph to see the association scheme? We have pairs, so the maximum distance is 2. Because, of course, if I have pairs, they differ at most in 2. They are disjoint. So we need the body diagonal, and we need another color, the blue. So maximum this, again, we get a strong regular graph as the one before, but this is 3-dimensional one. And I'm not mentioning that, but this is, of course, a Platonic solid, the diamond one, that is the octahedron. Great. So I'm saying an association scheme, like the Johnson scheme, let's say one of these, is actually a Platonic solid, one of the most famous ones. Okay, so here I'm just explaining what I say. Since K is equal to, actually for every V, we understand this, whatever is the alphabet actually, the number of the guys in this population, if I want to consider like pairs, I will always just 2 colors because of this bound, let's say on the maximum distance. So in this case, color depends on intersections. Okay, here I'm just, let's say, always extracting this graph to see better each of them. Again, so this is what I said, like the neighbors 4, 1, 2, always 4 for any of them, and you will see that there is a unique antipode. Yes.
The Johnson graph, the insert graph.
That's good. So, yeah. Yeah, bravo. No, okay. So when we consider Johnson scheme will contain, Johnson scheme is a set of graphs, let's say that every scheme actually. So the neighborhood graph is called Johnson graph. The complement one, let's say actually the maximum distance one, we call it Kneser graph. So the Kneser is the blue one. And it turns out, now we will see the next slide, that the Petersen graph is the Kneser of some. Yes, it is.
That's on the red.
Okay, I understand what you mean. Depends on the definition, let's say. Okay, in my view, it is Kneser, but actually they're just complementary to each other. It depends how you define the relations. Okay, but yes, we are there. So let's say in my language, this is Johnson, this is Kneser, maximum distance graph. So the neighborhood graph is called Johnson scheme, and the distance, the maximum distance in this case 2, is called Kneser. Okay. Again, this I'm just explaining how we connect and how we pick the colors here according to the distance. So again, just revealing what I said, octahedron then with its diagonal form one of the most intuitive, actually the most intuitive association scheme belonging to the Johnson scheme family. Yes, again, this is again to be attentive, like attractive. It reveals hidden regularity behind how we choose groups, okay, but more. So Johnson scheme, this is very interesting for me, are strictly related to the shapes that we actually can observe around us in the nature, not only in the nature, actually, also in the buildings. A lot of space frame get inspiration from combination of Platonic solids. This is crazy. Next time, I don't know if we will get there, look like deeply at some specific roof of massive building, like, I don't know, stadium, okay, space station, I don't know if you have this chance probably to see it, maybe yes, but I don't know, airport roof, they are made of these octet rust that are combination of some Platonic solids. That's why, and this is symptom, let's say, synonym of stability. Okay, whatever. Again, as always, we want to define this Johnson scheme in general, so we go beyond, we scale again the octahedron. Yeah, I won't have time, I guess, but at least I will reach that point. Okay, so as I said, Johnson's scheme, we understand from this very easy example, is the golden standard for now another kind of design theory, distribution, let's say, theory. What is the word? It's made of all the k subsets, so sets of size k, of a set, population of size v, and the color classes. So I'm just generalizing what we've seen in this diamond example. Don't laugh. Please. So two sets form an edge of color I if they share exactly k minus I elements. So for k equal to whatever is v, we understand that we have two colors then, two relations. Because of course it is two. I, let's say, runs from, we don't need to consider identity relation, of course. Let's accept that one. I will be runs from 1 to 2. So 2 minus 1, so they are in color, they are colored by red if they share one element, then 2 minus 2, 0. If they're disjoint, we use blue or any other color. Okay, here's some notation, technical one, let's say. Yeah, it turns out that this should ring a bell, actually, that these two are equivalent. It's the same, in fact, we know from binomial coefficient theory, counting, and it turns out that also graphically speaking, let's say association scheme-wise, counting k subsets of a v set is the same as counting v minus k. So we expect that to be equivalent, but still, this is just a hint to say, okay, it works. Okay, this is just an excuse to say, actually, that in our theory we assume this. We don't need to consider all possible k, but this relation is enough, just to avoid to get the same graph at the end of the story. And in fact, now we understood that, of course, v choose k is the size of our word, and the colors depend on the intersection k. But actually, the size of the subsets. Okay, now in light of this octahedron is the Johnson scheme with v equal 4 and k equal 2. Oh, I didn't mention, of course, the cube is also a Platonic solid. It was this in the Hemian scheme. But just to, we are getting there. Okay, so this is for you. Red graph, Johnson graph, neighborhood graph. The blue graph, so this is because they belong, all of them belong, this distance graph belongs to this family of association scheme. Kneser graph, complement graph, let's say. But complement if we have, it depends, of course. Whatever, okay. Matter of notation, okay. Yes. Yes. So now a question I already revealed, maybe already seen. What is J52? Okay, maybe we can't see like immediately, but this is the hint for me fundamental. As I said at the beginning, bravo, exactly. So when you don't know an answer, but you are like supposed to answer, it's Petersen graph, okay? So this is the hint. The only guy that now we met on our way with 10 points and 2 colors was the Petersen graph. So as I said, that's what's happening. Okay, so technically speaking, so maybe it's dual to yours, but this is Petersen graph is the Kneser of this scheme. So what does it mean? It's blue to some Johnson graph complement. Maybe you remember that at the beginning I said, let's pick the Petersen sum and let's use the red to color this. And then we colored with the blue the remaining lines to make it complete. Here, like it appears it's swapped, but it's okay. As we said, like the important is that we get 2 different colors to highlight the different distance regularities. And within this context, it turns out that the Petersen graph is actually the blue to a neighborhood one. But just an observation. Okay. This is actually where our journey should start, but it's okay. Yes. So this is applications. As I said at the beginning, beauty means, I will never stop saying these things, means beauty or symmetry in the nature, means regularity, but mostly stability, efficiency. That's why nature, like more like smartly than us, goes for it and say, but organize the shape that we are surrounded with using these Platonic solids. And actually these were like, association schemes, let's say more in general. And this was like widely understood, right, by the most intelligent maybe civilization like Greeks. They couldn't really explain the scenes phenomena, but they understand, they have this kind of intuition that we could use Platonic solid to explain the fundamental elements of the universe. But there is a reason. I mean, for me, it's found. After what I realized and discovered, it makes kind of sense. Maybe we don't have time to do this, but it's a pity. Let me just show you what's going on. Okay, let's say this is the last slides, but actually what I did, so after it, now like the funny part comes in the sense that, so less mathematics in the next slide, so maybe it's not actually really interesting for you. But I prepared a slide for each of them and see what is the natural impact or human impact. How do we use these shapes, or how nature uses these shapes, or how do we know we use shapes like this? Vabbè. Okay, this is just again properties. And this last one just highlights the fact that the things that I said, that most of them, actually not really, but see. In this, it's hidden the fact that most of them actually are related to Johnson scheme. Okay, let me say it better. There are things that are fact that are known to you, I think. Okay. Okay, first of all, if you check the numbers, you can see that there is a kind of duality relation between some of them. The first is self-dual, but here we have the same number if we swap these two. And this operation means interchanging places with vertices. And will give us some duality dual of a Platonic solid. It's still a Platonic solid. So it turns out that tetrahedron is self-dual, cube and octahedron are a dual pair, and the same for ico and dodecahedron. Okay? This is interesting, and this is how we reveal that actually Johnson scheme is there. Clashing the Platonic solid. So if we squash, we press the vertices, let's check on the cube. This is also very interesting. Onto a plane perpendicular to any of the body diagonal. I don't have, now it would be nice to have like one in my hand to show you, but I see this. So if I line this figure in front of me, what I do actually, I put this in front of me, aligning these guys on the diagonal, let's say, I can collapse this on a plane, so making this coincide with the center, and I get an hexagon. I have like, later there are this animation of showing that, but maybe we don't have time. So if I merge every antipodal pair of the icosahedron, then we recognize this is actually an equivalence relation. So it's not that visible, not so obvious, but it is possible to see that if we merge the antipodal, so we identify the antipodal pairs, we get the symmetry of K6, complete graph on 6 vertices. This is not in then J61, the way of picking one element out of 6. Of course, when I say this is the way, when we put one here, every time this is the way to make complete graph from the Johnson. And if we apply the same to the dodecahedron, we get the Petersen again. So that's why I'm saying that actually all these Platonic solids comes from one association scheme or are related to that. Okay. I think ran out of time or what? No, I think it's too long. Okay, I will just let me give you some pictures, images. This is just to have fun. It's a pity because I prepared many things, but it's okay. Oh, that's what I prepared, but I don't know why I did like this. Okay, let me go back. This is for the next talk. Vabbè. Just the general one. Okay, this is the general page, and then we stop here. But what I say, I went through each of them, like let's look at them closer, let's say, and see the application in nature or in human buildings, whatever. Okay, so this is the story, this is the definition, and just using the definition, actually, it's possible. I checked many proofs. There is a very nice one relying on what is called Euler equations that easily can tell you that you can have just the numbers, the combination that we seen in the previous slide. So there are exactly 5 Platonic solids. According to the definition, because of the definition. You can, from the definition, you can kind of derive, I don't remember now which one, you can derive some Euler equation that represent the relation between number of vertices, edges, and faces. So you are forced to have these 5, just trust me. Here a bit of history. So why Platonic? Because Plato was the first philosopher, actually the first one to mention them in his dialogue, Timaeus, and associating them with 5 elements, the fundamental 5 elements. That's the reason why that's those pictures, this representation. So fire is tetrahedron, earth cube, air octahedron, whatever. Okay. even Kepler, this is interesting, tried to explain, failing at the end of the story, the solar system using a nested model of these Platonic solids. Actually, I didn't explain, but let me go back because just to show you the pictures. This is what he proposed. Somewhere, I don't know where I put it. This guy. It's not super visible, actually it was super hard for me as well, but we have this nested, I don't remember the order, but you can kind of recognize that, okay, of course, this is the tetrahedron, this is the cube, but inside we have icosahedron, dodecahedron, like one inscribed into each other, separated by some spheres. And they wanted to use this to explain the distance between the planets, but this kind of justify his theory, in the sense that at that time, when he proposed this model, there were just 5 extraterrestrial planets known. So that was like, oh, maybe we can interpret this in this way. Okay, he failed in this like masterpiece that actually he wrote, because in the same book, well, no, masterpiece essay, he actually gave rise to the very famous tree law. That way, they are still like something that we rely on. But okay, let me go to this and then we finish. Okay, and what I'm saying, we are using them as association scheme to solve like problems in coding theory, crystallography, biology, meteorology, a lot of things, many. These are just some example of architecture that get inspiration from this. Yeah. Yes, also, of course, their foundation, let's say. That's a bit exaggerated in gaming and puzzles. But actually, there is more, trust me. So, but I think I have to finish here.
Thank you, Giusy, for a very illustrative and interesting talk. Any questions, comments?
Okay, maybe I can show you the other slides.
Sure.
Just showing one quickly. For me, this is like the things that blow my mind. So Tetra Pak takes name from this, the tetrahedron, yes, because they were like the way they shaped the first milk containers. Actually, some of them are still around. I mean, at least at home I have some small portion of this, like for kids portion, still comes into this shape. This is synonym of like minimum amount of, that's why efficiency. Minimum amount of packaging, so very like zero waste of packaging material for strong resistance, let's say. This is like, also in methane or tetrahedron, so you tetrahydrate, you can meet this kind of shape. Okay, but here I could continue like for the life, the same here, a cube, many things about cubes. Let me just show you quickly, nothing. Just take a look. Just because it's beautiful. Okay. Salt. Yes.
Or just with the justice.